now changing electric charges, you can have processes that involve the weak force where the electric charge changes. So it seemed like they were all dancing in the same ballroom, and it was natural to try to bring it together. Glashow said, well, this is probably what you need. You probably need this photon going along with these two W bosons, which are charged, but there should also be this Z boson, which should be neutral. But he couldn't quite figure out how to put it all together in a consistent way. What Weinberg did was he took those papers from 1964 that people had been using to, we now talk about with the Higgs mechanism and all the, discovery of the Higgs. Weinberg took those papers and took the mechanism they had for giving mass to some of these bosons, and he incorporated it into the ideas of Glashow and people like that in terms of bringing these two forces together. And he created this consistent theory.
And what I particularly like about it was that he wasn't actually thinking about this initially. He was thinking about the quarks. He was thinking about the strong force. And in his calculations, he was finding that he was predicting a massless particle, which was the pion was massless. But he knew the pion wasn't massless, so it wasn't working there. And at that time of his life, he had young children. He was out looking after them quite often because his wife was working as well. And when he was out, he was thinking about what's going on. And he realized, actually, maybe I could apply this formalism to the weak interactions and electromagnetism, because we know the photon is massless.
He had these four sort of force carriers, the photon and the three carriers of the weak force. He needed to make three of them heavy. And so he realized that meant that the Higgs particle that he had to introduce into the game to make them heavy had to be able to give 3 degrees of freedom to the 3 heavy bosons. And then there would be 1 degree of freedom left over, which would be the Higgs that we see. And it's exactly the physics that we see.
So this new theory, which was unifying the weak interactions and electromagnetism, predicted the existence of what we call weak neutral currents, or the Z particle, it's called, which was the initiator of an interaction between, if you had an electron and a neutrino and they scatter, so in comes an electron, in comes a neutrino, and they scatter, the mediator which allows for that scattering was this neutral current, which included the Z particle. And it was a prediction in this 2.5-page paper, beautiful, beautiful paper. And he didn't really believe, he knew it was good, but he didn't really believe that it was, he didn't really think it's going to be a description of nature. And this is really interesting because he didn't know at that time whether this theory, which we call the electroweak theory, was what we call renormalizable. What does that mean? Renormalizable means that you can take all the infinities which often occur in quantum mechanics, in quantum field theory, and properly absorb them into physical quantities so that you end up with a predictive theory. If you have something that gives you an infinity and you don't know what to do with it, then how do you know how to believe any of the finite results? Renormalization is the technique which allows you to properly absorb them, that's called the regularization bit, and then make a prediction for a finite quantity. He didn't know if the theory was renormalizable. And it wasn't, and so this model got very little attention. If I remember right, it only had, for about the first 2 or 3 years, 3 or 4 citations.